So as we hinted about on Tuesday, we're going to learn how we can look at the periodic table and see the electron configurations for the various elements. So here's a term that we need to be familiar with, valence electrons. We need to understand what that means. The valence electrons are those in the outermost principal shell. So we talked about the principal shell being n equals 1, n equals 2, n equals 3. So whichever the highest one is that has electrons in it, those are the valence electrons. These electrons are really important because those are the ones that are more on the outside of the atom, and those are the ones that are involved in bonding and forming ions and interacting with other things. So those are really important. The electrons that are not valence electrons are called core electrons. So we divide the electrons into two groups, the core electrons, which are on the inside, and the valence electrons, which are on the outside. So here's an example. We look at silicon, and silicon has a total of 14 electrons. Okay, and here is its electron configuration, 1s2, 2s2, 2p6, 3s2, 3p2. To figure out how many valence electrons it has, we look at the highest number here. The principal energy level or principal shell number 3. N equals 3 is the highest. And so in all the orbitals in that shell, we count those as valence electrons. So there are 2 electrons in that s orbital. And there are 2 electrons in the p orbital. And so we say that silicon has a total of 4 valence electrons. All the other electrons are called core electrons. So there's 10 core electrons in the first and second levels, and then there's 4 in the highest level. Yes?
Does the valence electron listing, does it change depending on the amount of electrons that are in that particular element? Like we'll always start with S, 3S.
It would always start with S because S is the lowest energy orbital or subshell in any shell. So that one's always going to get filled up first.
I mean, like let's say that we have like arsenic or something, or selenium is like 34.
Mm-hmm.
And so will its valence electron start at the same point of 3s2? Everything else from that point forward out will also
no, arsenic would have electrons in the 4s2 and 4p levels. So it's whatever the highest number is.
Oh,
okay. These numbers, the n numbers, 3. So, we learned this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and blah, blah, blah. Whichever the highest number is, you count all the electrons in that level, in that shell, and those are the valence electrons. Yes?
So if you were in like potassium, you'd only have 1 valence electron.
Right.
To 4s1.
Mm-hmm.
Okay.
So let's write an electron configuration for chlorine and identify which are the valence electrons and which are the core electrons. So chlorine has a total of 17 electrons. See that from the periodic table. So we've got 17 electrons. So first is the 1s orbital, and that can hold 2 electrons. The next orbital in energy is 2s, and that can hold 2 electrons. The next is 2p. There are 3 2p orbitals. They each hold 2 electrons, and so there can be a total of 6 electrons there. And then we get to 3s2. That one's going to be full. And then 3p is the next one. And that one's going to have 5 electrons in it. So 2 plus 2 is 4, plus 6 is 10, plus 7 is 17, and that's the right number of electrons. So there's the electron configuration. That's what we learned how to do on Tuesday. And now we look and we see, okay, 3 is the highest level. 3 is the highest level, so all the electrons in that third level are considered valence electrons. So 2 plus 5, there's 7. 7 electrons. So sometimes we abbreviate that VE, valence electrons. Not victory in Europe, but valence electrons. Because this isn't history class, this is chemistry class. I was forced to take history, though. Okay, so then these guys over here are the core electrons. So there's 10 of those.
Which is why one electron.
Pardon me?
So that's why it would be one electron. And not one
That's why chlorine wants to gain 1 electron to get 8. Yes, you're foreshadowing for me. Thank you. We're going to get to that. Any questions about identifying valence electrons? Okay. Let's look at another one here. Selenium. Selenium has this electron configuration. Okay, so it goes blah, 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 blah. And so here we've gotten into where the order gets kind of mixed up. We went over that on Tuesday as well. But we're going to look again at the highest number. The highest number is 4. So the electrons in this 4s shell are considered valence electrons, and in the 4p, but this is 3. That's a 3d. Even though it is higher in energy, it's not considered a valence electron. Okay? So you look for the highest numbers, 4, count up all the electrons in that 4th level. So selenium has 2 plus 4, or 6 valence electrons. Everything else is considered a core electron. Okay?
If you wrote it, that's how you write it, with a 3D10 in between the 4s2?
Mm-hmm.
Oh, okay.
Because the 4s2 fills first, because it's lower in energy.
Okay.
And yet it's a higher principal quantum number. So this is a little tricky because without thoroughly explaining quantum mechanics to you, it seems like there's some holes in this. And so just take it at the face value.
So it'll fill those 2 electrons on the outer shell first before it fills in the 10 on the inner.
Mm-hmm. Yeah.
Because for some reason just 2 on the outer is less energy than 10 on the inner.
Well, the 4s energy level, the 4s orbital, is lower in energy than the 3d because of how all those electrons are interacting with each other. Okay, in a single electron atom like hydrogen, all these levels exist. They're just not occupied. And with hydrogen, where there's only 1 electron, the 4s energy level is higher than 3d. But we don't even need to know that because it has only got the 1 electron, and that 1 electron is going to hang out in the 1s orbital, which is the lowest energy. I have a weird analogy involving a hotel, and it's helpful for some things. You know, a lot of hotels have multiple stories, and so the floors are like the energy levels, okay? The rooms exist even if no one is staying in them. The people are like the electrons. And so even though a room is vacant, it's still there, and an electron could move, a person could move into that room, even though they are not in there now. Yes?
And you can think of like the 3D as like a suite. It's actually better than the...
Right, it's not on the higher floor, but it costs more money.
Yeah.
Okay? And so people go up and take that little room on the 4th level before they take the more expensive room on the 3rd level. It's a suite because it has 5 beds in it, and each bed can hold 2 people. Well, it's great for a big family like mine. We end up having to get 2 hotel rooms. It's not a good thing. Okay, so if you're interested in my analogy, I can share that with you later. Yes, I'm fine with that. I know you can't synchronize with Evernote. So here's a section of the periodic table. We've taken the first 3 rows and just squished them together. And what they're showing us is the valence electron configurations. So for lithium, the highest level is 2, and there's 1 electron in there. You could also think of these as the noble gas shorthand, where this would be helium plus whatever is listed here. And this would be helium plus that. And this would be helium plus this. Okay, so the core electrons are the ones in the previous level, and these are the outer, the valence electrons. What do we notice here as we go down here? Hydrogen, lithium, and sodium all have an S1 as their last term in their electron configuration. That last electron that gets added is in the S orbital. And we go to the next column, and these guys are all S2. And this is, helium and hydrogen, they're like little brothers, and they're exceptions. So, we look at helium and we say, well, maybe you should be over here next to hydrogen. Well, in some ways he should be. I could make him be over there. I just realized that. I like being able to draw on the slides. So you could imagine helium being over here as well with a 1s2 configuration. 2s2, 2p1. And aluminum is 3s2, 3p1. Let's go over here. Fluorine, 2s2, 2p5. Chlorine's right underneath. The only difference is that those electrons are in a higher level. But it's the same arrangement, 3s2, 3p5. You see there's something in common with the columns, the families in the periodic table. The elements in the periodic table, their electron arrangements are similar. Now, if we look at group 1A here, how many valence electrons does hydrogen have? Well, it only has 1 electron, so it's got 1 valence electron. How about lithium? It has 1. And how about sodium?
1.
It has 1. And what group number are they in? 1. Let's go over here, nitrogen. How many valence electrons does nitrogen have?
5.
How about phosphorus?
6 or 5.
5. And what group number are they in? 5. Oh. Fluorine, how many valence electrons?
7.
And chlorine?
7.
And what group number?
7.
How convenient is that?
Seems like someone set it up that way.
It's like someone set it up like that.
Helium's not going to play ball.
Helium is the baby brother. If you put helium over in group 2, so you just have to watch out for those babies of the family. It's like my little Andrew and his Angry Bird hat this morning. And yesterday, I could understand that. It was cold yesterday. You don't really need to be wearing a hat, but he won't wear long pants. He's wearing shorts and a T-shirt, but he has to have his Angry Birds hat. Makes sense? Yeah, well, good. Maybe you could explain it to me later. So that statement there, the elements in the same column all have the same number of valence electrons and similar outer electron configurations. The number of valence electrons corresponds to the group number when we use the 1A, 2A type group numbers. That's why I don't like these periodic tables. They use the other type of group numbering system, which in some ways make more sense. Just, start at the left and count all the way across, 1 through 18. We talked earlier about how elements in the same family have similar characteristics, similar properties. They react in similar ways. They do that because their valence electrons are similar. They have the same number of valence electrons. So let's look at this. These are the outer electron configurations of all the elements in the periodic table. Can you see those? They're kind of small. And here is the pattern in the periodic table, and they've color-coded this for you. So over here, these columns, where are the valence electrons? They're in the s orbital. And the pink guys over here, where are the valence electrons? In the P. Pink. P for pink? I don't know. That just occurred to me. And these guys in here, they all have electrons in the D level. Okay, so these are considered D block elements. Now, we're not calling those valence electrons. And the transition elements we saw with their charges as ions are kind of unpredictable. And they don't always get on board and follow the pattern here either.
Why don't the outer shells of those act the same as the other ones?
Well, they also have those D electrons in there as well. And so that kind of makes them act differently. Yes?
Does the identification of S, P, D, and F, do they mean something, or is it just kind of...
Yes, those letters do come from a description of the spectral lines. I need to look up what S is, because every time I lecture on this, I'm like, I don't know what S is. P is for principal, D is for diffuse, and F is for fine. And I don't remember what S stands for. I need to look that up. But those came from a description of the lines. And then they just kind of stuck because people had been using them. So they don't really make much sense to students. They seem pretty random, and yet they're not actually random. That's a good question.
So why does zinc and gold have set charges when, like, copper has the same one electron in S orbital, like gold has the same
I think you're meaning silver.
yeah, that's what
Yeah.
I said.
So silver and zinc each only form an ion with a particular charge. They only form one kind of ion. We learned that. But the rest of them form more than one ion. And why is that? That's very complicated. That's very, very complicated. Definitely beyond the scope of this class. It has to do with these guys. Oh, shoot, I keep forgetting I can't point on that part of the screen. These guys in here, if we count their valence electrons, like vanadium, how many valence electrons does it have?
5.
2. Because only the 4 counts. And we go over here to cobalt. How many valence electrons? 2. So most of the transition elements have 2 valence electrons. And they do have similar characteristics. They're all metals. They form positive ions. And yet they're not all exactly the same. And then there's some interesting anomalies in there as well. Any question? No?
Mm-hmm.
Yes.
Oh, no.
You look
Is there a
like
mnemonic device for remembering where everything goes in here?
well.
Do we need to know that, or is that just...
The shape of the periodic table itself will really help you out here, because how many electrons can an s orbital hold? 2. There's 2 columns there. And the p subshell can hold how many electrons? 6. And the d subshell can hold how many electrons? 10. And we haven't talked much about them. The f, they can hold 14. And so it's all in there. And if you think about building atoms, and you start with 1 proton and 1 electron, and then you add another proton and you add another electron, and you just keep doing that, you can see that going from potassium to calcium, we've added 1 electron, and that electron will also go in the 4s2. And then when we go to scandium, we're going to add 1 into the D, and titanium adds another 1 into D, and vanadium and chromium. And so you can think of this as you're just building up. And that actually shows you the order. There's slides coming up that are going to state this as well. I just have a hard time seeing on this little tiny screen. I'm going to look over here on the laptop. Do you remember period numbers? The periods are the rows in the periodic table. Those are numbered 1, 2, 3, 4, 5, 6, 7 down the left side. Okay, here's sodium. What is its highest shell?
3s1?
3. It's in period 3. How about boron?
2.
2. It's in period 2. How about strontium? 5. It's in period 5. So the period numbers correspond to the highest principal shell for those elements. And then the D thing is it's just a little weird. Doesn't it look like this part of the periodic table sunk down? Because here we've got hydrogen and then beryllium, and it looks like this level should be here, doesn't it? Like you were going downstairs, but there's this jump, like it fell. So these d orbitals are the period number -1. And in my little fantasy chemistry world, I think of these as originally they should have been up here, but they fell down. And that's why the d number is 1 less than it is over here. So these are filling 3d. They're in group 4, period 4. 4 minus 1 is 3. Down here, wolfram, tungsten is filling 5d. Well, it's in period 6. 6 minus 1 is 5. So the number of the principal shell comes from the period number on the periodic table. And the particular subshell, whether it's S, P, D, or F, that is the last one being filled, comes from which section of the periodic table that element is in. Do you see that pattern? You had some nodding and some blank stares.
Yes, I see that.
Thank you. So the number of valence electrons for any of the main group elements, except helium, is equal to the group number of its column. We mentioned that earlier. And in case you've forgotten, the main group elements are groups 1A, 2A, 3A through 8A. Those sections that stick up, those are the main group elements. So we can look at sulfur and see it's in group 6A and say, oh, 6 valence electrons. Now those other numbers, 16, is that related in any way to 6A? Well, 16, 6A. Those other numbers without the A's, if you take the 1 off the front, it's the same. So group 15 is group 5A, 5 valence electrons. Group 17 is group 7A, 7 valence electrons.
And then then you have 10 core electrons?
Yes.
The other number would be 10 core?
Yep. So if you look at, say, sulfur, and it has 16 electrons, and we can see from it being in group 6A that it has 6 valence electrons, well, 16 minus 6 leaves us 10 core electrons. So everything else is core electrons.
Just minus the column from it.
Mm-hmm.
Okay.
And the row number in the periodic table is equal to the number of the highest principal shell. That's the n value. So we've talked about how these orbitals are designated by the principal shell number, n equals 1, 2, 3, 4, etc., and by a letter, S, P, D, or F. So let's look at, silicon. So it's got 4 valence electrons, and we can see in its electron configuration here, it's 3s2, 3p6, 3p2. 2 plus 2 is 4 valence electrons. And those are in the 3rd principal shell. It's in period 3. So let's do lead. How many valence electrons does lead have? What group? 4. It's in group 4A. And what level are those valence electrons in? 6. Okay. So it's kind of like this grid map thing that tells us a lot about the electrons in these different atoms. So the main group elements are nice and predictable. The transition elements, not so much. Transition series represent the filling of core orbitals, and yet the number of valence electrons is mostly constant. So if we look at, I wish that had numbers, 1, 2, 3, 4. If we look at period 4 on the periodic table, actually let me just go through this real quick and then we'll look at it on the periodic table that's coming up next. So there's 2 exceptions in the first series, and those happen because a half-filled d orbital is especially stable and a completely filled d orbital is especially stable. The principal quantum number of that d orbital being filled is the period number -1, the row number. So let's look at these guys. So here we go. When we get go from calcium to scandium, we see that the valence electrons are staying the same for S2, and now we're filling up the 3D level. This is period 4, and so the D subshell that's being filled is for -1 or 3. So we go, here's D1, D2, D3, and then we're like, wait, that should be D4. What happened? Well, one of the electrons left the 4s orbital. Now we only have 1 there, and it came over to fill up the 3D halfway. The D subshell can hold 10 electrons.
And isn't the D more stable than the 4s?
Having the D half full is more stable. Okay, so in the hotel analogy, there's a special that if you half fill that D suite, you get a discount. And so somebody from that the lower expensive room, the 4S, is going to move into the 3D because overall you're going to save money that way. And so we've got that one as an exception, chromium. And then we go along and here it went back. Now the next electron goes back into the 4S. And we still have this half-filled D. And then they keep on with the pattern. D6, D7, D8, and then we have another oops. Because if the D is completely full, there's also an energy bonus. And so that's going to fill up the D orbital and leave the S orbital half full before it goes on, and then over here, now the next electron will go into the S, and both of them are completely full.
So does that at all affect the kind of ions it makes?
A little bit, but not really. The types of ions that the transition elements make, I remember studying that in college, and it didn't seem important to retain in my memory. So honestly, I can't tell you other than there is physical chemistry explanation for why they form the ions that they form. I mean, there is some reason, but it's not any simple reason that we can get from the periodic table or just looking at electron configurations. It's just unpredictable. Yeah. It's a good question, though. So, having looked at these patterns in the periodic table, writing electron configurations becomes much easier. So if we say write the electron configuration for phosphorus, we can do this based on its position in the periodic table. So here's phosphorus, and if we're going to use the noble gas configuration or shorthand, we're just going to go up 1 level to the end, and there's neon. And so we're going to write neon in brackets because this is neon plus. And then we're going over here, and all of these things are going to be filled up. So this would be the 3. This is the S block, and there's 1, 2 electrons, so 3s2. And there's nothing here, so we skip over that. And we come over here, and this is the P block, and it's still in the 3rd period. So 3p1, 2, 3. And so neon 3s2, 3p3 would be the electron configuration for phosphorus. And with a little practice, you can just read it off the periodic table. Does that make any sense? So here are the book's little guidelines for writing electron configurations based on position in the periodic table. Represent the inner configuration with the symbol for the previous noble gas in brackets. The outer electrons are going to be determined from that element's position within a particular block in the periodic table. The highest principal quantum number is equal to the row, the period number, and those d electrons are going to be the row number -1. So let's determine the electron configuration for tin. Well, first we have to remember what's the element symbol for tin? Sn. Okay, so then we need to go find Sn in this table. So here it is. So the previous noble gas is krypton. So we're going to put krypton in brackets. And then we're going to see, okay, well, what comes after krypton? Well, here we've got, this is period 5. Period 5, these are two s electrons. So I'll write that in. This is period 5. That's the s block, and that's being filled up. And then after that comes the d block. The d block is full with 10 electrons, but that's not 5d, it's 4d. So 4d, 10. And we keep going, and we get over here into the p block. This is 1, 2. There's 2 electrons there, and so that's 5p2.
We count 10?
Yes. And see, it's on the periodic table, and so if you don't remember the 2, 6, 10, 14 thing, it's on the periodic table. You can actually just count them. There's 10 across there.
So it has 4 valence electrons?
It has 4 valence electrons, yes. Because the valence electrons are the ones in principal shell 5. And there's 2 in the s orbital and 2 in the p orbital. And those 4 d electrons are considered core electrons. Let's do another one. Somebody pick an element. Gold. Okay, let's do gold. So gold is Au, because if someone takes your gold watch, you say, "Hey, you, come back with that." So we need to find gold. Let's, oops. So here's gold down there. And what's the previous noble gas? Well, it's xenon. So gold will be xenon plus, so from xenon, we come over here. This is period 6. So this is 6s2. And then this is in here, this is going to be 5, right? 5d. We would predict that it would be 5d9. That's what I would expect you to predict. In actuality, though, the 6s, one of those electrons goes over here, so that one can be completely full and the other one can be half full. I do not expect you to remember, like for a test, I will not ask you and expect you to remember those little glitchy exceptions, okay? I tell you about them because you might notice them and say, why is this? And there's a reason behind it, but I don't expect you to remember that. And I'm not going to make you, on an exam, do any electron configurations involving the f orbitals. Okay, that's just more than we need to deal with. Any questions about that example? Yes?
What's the valence electron?
Valence electrons for gold. Well, looking at that electron configuration, what's the highest level? 6, and there's only 1. Yeah. So most of the transition metals have 2 valence electrons. Some of them have 1. Okay? And I'm not gonna get you on those guys.
Give you on this chart, why don't they give you the valence or the electrons for those last ones on the? They just not have those, or?
You mean these guys at the bottom?
Yeah, are they just no? Right there, 107.
Oh, these?
Are they just so complicated? They just don't.
Where do they stop with that?
107.
Yeah. If you look on the periodic table on the wall, you see that all of those are in white. Those are man-made, and they're unstable. And, yeah. So could you write electron configurations for them? Yes, you could. I guess they just didn't feel like it. Yes?
So the only time, just go back to this, the only time when for D steals from an S is if it wants to be half full or completely full?
Right. D will steal an S electron to be either half full or completely full. Because that's just, it makes it more stable. It makes it lower energy overall. And so it's,
Other times, so if there's already 6 in D, that's...
It's only when it's 4 and 9.
pretty much, yeah. I think if we, let me zoom in there. There's some that are just kind of weird. Like niobium, number 41, does, ooh, there's a typo on that. You see the typo on this guy? Yeah, what is that? They put the 4 in the wrong place. But there's an exception with the half full, completely full thing. Why does it do that? Off the top of my head, I can't tell you. It's got to be lower energy, but for what reason, I don't know. Question?
Can we still count the valence electron, for example, gold? Do we use the 11 and then just take?
No, you can't. You can't use the group number for transition elements to count the valence electrons. It's for the transition metals. It's either going to be 0, 1. Well, I guess it can't be 0. It'll either be 1 or 2.
You can use the count the electrons that they have over the noble gas that has the core in front of it.
Well, we can do these guys over here, but those are main group elements. And we could try to look for some patterns and stuff, but I'm not going to ask you about it. So, you had a question?
I was wondering, since when the valence electrons, the higher that they become, in which there are more of them,
Mm-hmm.
the element is the element is that considered like a radioactive element because it is freely letting electrons go and gaining them and becoming less because it's trying to get rid of them. It's trying to
Are the larger elements radioactive because their electrons are in higher levels?
Yeah.
No, because an atom being radioactive doesn't have to do with it losing electrons. It has to do with its nucleus falling apart. And has to do with protons and neutrons and other ons coming out.
Mm.